let's talk about the reaction of alkyl halides with NaCN, which is the last type of nucleophilic substitution reaction. So for this, your reagents are going to be your alkyl halide and NaCN. And the conditions are going to be that this needs to be dissolved in ethanol and that you need to heat it under reflux. So what happens in this case is, since this is going to be a primary alkyl halide, it's going to go through the SN2 mechanism, but it's going to be the same as what we discussed for NaOH. So if you're confused about that, you can go scroll back and look at that video. So what's going to happen is that this CN and Br are going to interchange their places. So after the reaction takes place, the bromide ion is now going to be attached to sodium, and the cyanide ion is now going to be attached to this alkyl halide. So in this case, it's going to turn into a nitrile, and a nitrile is any substance in which the CN group is attached to an R group, which is basically going to be your hydrocarbon chain. So this is going to be called a nitrile, and this type of reaction is very important in organic synthesis because it helps to increase the length of the carbon chain. As you can see in this case, initially this alkyl halide has 2 different carbons, and after the reaction proceeds, the number of carbons increases to 3 and your functional group changes. So you go from an alkyl halide to a nitrile. And these nitriles can undergo various other reactions using which you can get different functional groups. So the first one that you have is hydrolysis. For this, you use dilute acids like HCl, and you're going to get a carboxylic acid. So in this case, what you have over here is a 3-carbon nitrile. So you're going to get the corresponding carboxylic acid, which is going to be propanoic acid, which is a 3-carbon acid. The next type of reaction that takes place for nitriles is going to be reduction. So for reduction, you are going to use a reducing agent. You can use 2 different reducing agents. The first one is going to be sodium metal in ethanol, and the second one is going to be sodium borohydride in water. And you are going to get the corresponding amine. So basically, as you can see, these 2 groups over here, this carbon and this nitrogen, don't have any hydrogens attached to it. So after using your reducing agent, since reduction is addition of hydrogen, 2 H's are going to be added to this carbon and 2 H's are going to be added to this nitrogen. Since the other groups already have hydrogen attached to them, they're going to remain unchanged. So this was the reaction with NaCN and the reaction of nitriles, which is the product of this reaction. Now we're going to be discussing elimination reactions of alkyl halides. This is the second type. The first one was nucleophilic substitution, which we have already discussed. So for this, your reagents are going to be the alkyl halide, and you also have NaOH, and you can also use KOH. And the conditions, these conditions are very important because they distinguish nucleophilic substitution reactions from elimination reactions. And the conditions are that this needs to be dissolved in ethanol and you need to heat the mixture. So the mechanism for this reaction is not in the syllabus, but what you need to know is that you get the corresponding alkene. So in this case, since you have a 2-carbon alkyl halide, you are going to get a 2-carbon alkene. Now the way to figure out what alkene is used is basically to first mark the carbon atom that is attached to the alkyl halide. So I've highlighted that over here. After that, you look at the adjacent carbon atom and you look at the hydrogens that are attached to that atom. So in this case, these 2 hydrogens are attached to the carbon, to the adjacent carbon. And what you do is you remove any one of these hydrogens to get the corresponding alkene. Now let's look at a specific example. Now over here, you have this 4-carbon alkyl halide. And the carbon that I've marked over here, this is going to be the carbon that is attached to the Br group. So as you can see, there are 2 carbons which are adjacent to this one. One of them is on the right and the other one is in the left. So now this carbon, the one that I've highlighted again, this carbon has two hydrogens attached to it. The first thing that you can do is remove one of these hydrogens, and this is going to give you this product. What else you can do is remove a hydrogen from this carbon, which is going to give you this product. So as you can see, this is going to be your first product, which is going to be in a lower yield, and this is going to be your second and third product. The reason why I've written down it's going to be second and third is because this can be cis and it's going to be trans, and I'm going to draw out the cis and trans for you. So this is going to be the cis arrangement. And this is going to be the trans arrangement. So right now you have three different things. You have this one, and you have cis and trans. So you have three different products that are forming from this reaction. So this was elimination of alkyl halides. In order to determine the rate of hydrolysis of alkyl halides, we take the alkyl halide and we dissolve it in water, and we also add ethanol and silver nitrate. This reaction takes place in two steps. So in the first step, your alkyl halide is going to react with water to form alcohol, and it's also going to form a hydrogen halide. In the second step, the hydrogen halide is going to react with these aqueous silver ions to form this precipitate. And the time taken to form this precipitate is going to determine the rate of hydrolysis. So now let's look at an example. In this case, we're going to be using three different compounds. So the first one is going to be CH3CCl. The next one is going to be CH3CBr. And after that, you're going to have CH3CI. And now we're going to look at the observations. So in this case, it's going to be slight cloudiness after 1 hour. For the next one, it's going to be cloudiness after a few minutes. And for the third one, it's going to be thick pale within just 1 minute. So as you can see, as you go down this table, the time taken for the precipitate to form, this precipitate over here, for this precipitate to form is going to decrease. This is because the bond energies are decreasing. Now if you look at it in this case, it's going to take more time for the carbon and chlorine bond to break, because you need this chloride ion to form this precipitate over here, AgCl. Since it's going to take more time for this to break, it's going to take more time for the precipitate to form. In this case, it takes less time for the precipitate to form. That means that the bond energy between this carbon and this iodine is going to be very less. Since the bond energy is going to be very less, this bond is going to break faster and your precipitate is going to form faster. So we can tell that the formation of this precipitate is directly linked to bond energy. So like I said before, for this, the bond energy is going to be higher, and for this, the bond energy is going to be lower. We will now be discussing the properties of alkyl halides that makes them suitable for the following uses. So alkyl halides are very inert, unreactive, and non-toxic, which makes them very suitable for these users. So now let's talk about CFCs, which are chlorofluorocarbons. So in the stratosphere, because of these conditions, which is 250 nanometers and the energy from sunlight, this oxygen molecule is going to split into 2 atoms of oxygen. So naturally in the stratosphere, one oxygen atom and one oxygen molecule are going to combine to form ozone. And similarly, this ozone molecule is going to split back into oxygen and an oxygen molecule and atomic oxygen. This process is going to be in equilibrium, which means that the rate of ozone formation is going to be equal to the rate of ozone depletion. However, because of the use of CFCs, radicals like this chlorine radical are going to react with ozone to form more radicals. And these radicals are going to form even more radicals. So this is going to be a chain reaction. And because of this, the ozone layer, which protects us from UV light, is going to deplete. Because of this, CFCs are no longer used anymore. and you have other products which we will be discussing now. So CFCs were also used for aerosol propellants and coolants and anesthetics. For anesthetics, right now we use halothenes. An example of halothane would be CF3CHBrCl. They were also used in fire retardants, and right now we use halons. And lastly, they're used to make polymers like polyvinyl chloride or PVC. So these are the uses of alkyl halides.